Hello and welcome to our lesson on tangent and cotangent functions. So the parent form of the tangent function that we're going to start with today is just y equals the tangent of x. And we're going to go ahead and look at the graph. Although we have technology, we're going to make a table, kind of understand what's happening with the tangent function. But before we do that, remember that when we're looking at the tangent, we're trying to find the tangent of an angle. We write a ratio of like the opposite over the adjacent side, or we saw that with the unit circle that we could just write a ratio of our y value divided by our x value. Well, we also know that the y value in the coordinates where the angle hits the unit circle corresponds with the sine. So y value corresponds with sine. We also know that the x value in the coordinates where that angle hits the unit circle corresponds with the cosine. So if we're looking at y over x, and those correspond directly to sine and cosine, then we can write our tangent function in another form. So not only can we see y equals the tangent of x, we can also call this y equals the sine of x over the cosine of x. So we can see that both ways, both technically considered the same function, just like the reciprocal functions that we talked about before, having those two different forms. And I want to point out a typo here. I meant sine, not this sine, but this sine. I don't know if that was my typo or a autocorrect, but yeah. Alright, so let's go ahead and make our graph. Again, we're going to graph over the interval from 0 to 2 pi. Let's just take a lap around the unit circle, see what's going on. Now this one's going to be not as simple as sines and cosines because we're not just picking these values out. Now we have to write these fractions of the y's over the x's. But some of these will still work out nicely for us. So let's go ahead and start at 0. At 0 degrees or 0 radians, if we take the y value and divide it by the x value, we get 0 divided by 1, which is just going to be 0. So our tangent function is going to start at the origin. That's kind of an important one. And then let's skip around here. So if I take this y value over the x value, I don't necessarily want to graph those decimals if I don't have to. So let me just, on the side over here, if I took 1/2 and divided it by radical 3 over 2, I'm looking at 1 over radical 3, which is not horrible. I just don't want to graph that fraction or decimal if I don't have to. So let's skip around, see if we can find something nice. Let's go to, the very next angle, 45 degrees or pi over 4 radians, dividing the y value by the x value there. It's the same thing divided by itself. So radical 2 over 2 divided by another radical 2 over 2. That's going to get us 1. So let's put that in the table. That's a nice one. At pi over 4 radians, our tangent is going to be 1. And then the same thing is going to happen here that we saw happen at pi over 6. I don't want to deal with that. But let's go ahead and go to pi over 2. At 90 degrees or pi over 2 radians, when I divide my y value by my x value, now we've seen this happen a few times. 1 divided by 0, that's no good. Right? 1 over 0, that's going to be undefined. And so this undefined location here is going to show up as an asymptote in our graph. So we've seen, like I said, a lot of that before, so hopefully that's not too crazy. Okay, let's go ahead and keep looping around. I'm going to skip to my next 45-degree reference angle, 3 pi over 4. If I divide something by itself, again, I'm going to get 1, but in quadrant 2, that's going to be negative. And then when I go to pi, or 180 degrees, 0 divided by negative 1 is just going to be 0. And then I think we're going to end up with the same exact set of y values already starting to repeat here. So if we go to 5 pi over 4, we're going to have negative radical 2 over 2, negative radical 2 over 2. That's the same thing that we saw happen over here, something divided by itself. 2 positives are positive, 2 negatives is going to make a positive for us as well. And then if we go to 3 pi over 2, I'm just making a mess of my unit circle here. If I go to 3 pi over 2, or 270 degrees, my y value divided by my x value, again, we're going to end up negative 1 over 0, which will be undefined. If I go to 7 pi over 4, so here, we're dividing something by itself, but it's positive, negative, so I get a negative 1. And then I'm going to come full circle to 2 pi and land back where I started at 0. So remember, we have this pattern of repeating y values in all of the periodic functions that we've seen. But in everything we've seen so far, it's taken a full lap for the pattern of y values to repeat. But notice what happens here. We have 0, 1, undefined, negative 1. And then the same thing happens, 0, 1, undefined, -1. So instead of having a period of 2 pi for this function, our period is going to be 1 pi because that's how long it takes for these y values to repeat. So we have a smaller period than we've seen in all of our other trig functions. But let's go ahead and make this picture, okay? So we're looking at 0, 0, we have a point. At pi over 4, we're going to go up to 1. At pi over 2, we're going to be undefined. Let's go ahead and put that asymptote in our graph. Graph's not going to go there. And then we have a point at 3 pi over 4, so that's 1, 4, 2, 4, 3, 4. It's going to be right in the middle of pi over 2 and pi. Our graph's going to be at -1. And at pi, we're going to be at 0. And then at 5 pi over 4... Oh, I did not go far enough. Hold on. Pi, we're at 1. 3 pi over... Oh, yeah, I'm good. I'm sorry. Losing myself here. And my pen is frozen. Give me a second. Sometimes the tip of the pen, like, unscrews and then it's not working. Oh, it's registering now. Okay, we're good. Okay, so where was I at? Pi over 4, we were at 1, and then we had our asymptote. 3 pi over 4, we're at -1 pi, we're at 0. 5 pi over 4, that's going to be between pi and 3 pi over 2. We're going to go up to 1 again. Pen's still on, good. And then at 3 pi over 2, we're undefined, so another asymptote. And then, again, this is the same thing is going to be repeating here. So we're going to go to 7 pi over 4 and be at -1. And then at 2 pi, we're going to be back to 0. And then if I went another quarter pi, we'd be back up here, and we're going to see the same sort of pattern happening. But what is this graph actually going to look like? So if we were to not skip the values in between, what's going to be happening is the behavior that we would expect to happen when we have asymptotes in the graph. We already saw this happen with secant and cosecant. And in general, when we have asymptotes, the branches of the graph that are in between the asymptotes do approach. So we're going to see, and I'll even show you with technology if you'd like, we have an asymptote at pi over 2, and you could see that the branches at pi, let me go and graph pi over 2 so you can, oh, I gotta sneeze. Sorry. Oh man, I thought the sneeze was going to come out. Okay, so I put a vertical line in there at pi over 2. So you can just kind of see where I'm trying to look. You can see that the graph from the origin approaching that asymptote is increasing and is going to get infinitely close to the asymptote on the other side, decreasing. And then at 3 pi over 2, we have another asymptote. Again, branches on both sides approaching that asymptote. So that's what's going to happen here. Our graph is going to continually increase and get closer and closer there. And then on this side, we see it get closer here and closer here. These almost look like cubic functions in between the asymptotes, okay, but we have constantly increasing branches of the graph. So I want to point out again that our graph technically, I would say, starts at the origin. We can also say it's centered about the origin. If I was to continue this, we're going to see that. That is what one cycle of our tangent function is going to look like. So this is technically what one cycle looks like. Oftentimes, when we're viewing this, we'll view the one cycle that's centered at the origin. Again, let me show you with technology here. So that one cycle from -pi over 2 to pi over 2, that's typically what, like, it's what I'm holding in my head when I say one cycle. So when I say one cycle of the sine wave, hopefully you're picturing the sine wave from 0 to 2 pi. When we're talking about tangent, typically we want to visualize this -pi over 2 to pi over 2 as our one cycle. Alright, so that's what one cycle of our tangent curve is going to look like. Let's talk about some of these characteristics that happen in general. Again, this, like secant and cosecant, not a continuous function. Anytime you have a fraction, you have the possibility of the denominator being 0. We end up with, or have this possibility of asymptotes or undefined places in our graph. So this graph, not continuous. We have vertical asymptotes that create discontinuities in this graph. And they happen at pi over 2, at 3 pi over 2, going to happen again at the next odd multiple of pi over 2. So our verticals are happening at the odd multiples of pi over 2. That's the same place where our cosines were equal to 0. So this is where cosine is equal to 0, because that's the cosines are the x values that are in the bottom of our fraction. Anytime we have that 0 in the bottom, that's what happens there, right? And again, those cosines happen at odd. That's 2n plus 1 multiples of pi over 2. Again, in this expression, n is an integer. We've seen a lot of that, okay? So any place where cosine can be 0, again, the bottom of our fraction can be 0, we end up with that asymptote. Those are on our odd multiples of pi. Between those asymptotes, we have these pieces of graph. I often refer to them as branches of graph, but in our one cycle, or any cycle, any place between the asymptotes, the graph is constantly increasing, heading toward both asymptotes. So increasing graphs between the asymptotes, and they almost look like cubic functions. Again, the period is a little shorter than it was for the other 4 trig functions that we've talked about. It only takes pi radians for the y values to repeat here. And if we look at the x-intercepts for our tangent function, the x-intercepts, so we started at 0, again, that's an important one, again at pi, again at 2 pi, so at 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, and so on. Every time we reach that 180 degrees at half of our circle, we're going to hit the x-axis, so those x-intercepts are going to happen at n pi, every multiple of pi. Like secant, cosecant, we have graph that's going to go up forever and down forever, so we have no max, we have no min, we have no amplitude. Now domain is restricted. We see restrictions in the form of those asymptotes. So just like with ones we've seen before, we have to kick those out, restrict them, exclude them from the domain. So this domain is all x's such that our x's cannot be odd multiples of pi over 2. So we cannot be 2n plus 1 times pi over 2. And then the range is a little different. So in every other function we've seen before, we've had a restriction on the range. Sine and cosine had a minimum of -1, maximum of +1. Secant, cosecant were exactly the opposite, so above +1 and below -1. But if you look at the portions of graph between the asymptotes here, we're going to have a graph that goes down forever and goes up forever, which means there is no restriction on the range. So our range is everything from -infinity to infinity. And then tangent is going to be an odd function. Again, if you look at the one cycle here that's centered at the origin, we can see every point and its opposite. That's symmetry about the origin in that graph. That is the characteristic of an odd function. Or if you took the tangent of a negative angle, you're going to get a negative result. So that's again what creates that symmetry about the origin for an odd function. All right, so now let's talk about transformations. This is again what one cycle looks like. That's what you should be visualizing, although probably more common to visualize the one cycle centered about the origin. The transformation rules, okay? We can see A, B, C, and D in our general form, just like we've seen it before. So here's our general form with A, B, C, and D. And the same transformations would apply. They just don't apply with some of the specific terminology. So for instance, we talked about A. We know that when we multiply something there, it affects the amplitude for sine and cosine. Well, we don't have amplitude here, so we would go back to our generic terminology, meaning we would vertically stretch or compress the graph if we change A. And then B is still affecting the frequency. So normally, with all the other trig functions, the sine, cosine, secant, cosecant, we said we take our normal period of 2 pi and divide it by b. Well, here our normal period is pi, so we would take pi and divide it by b to see what the frequency is going to look like, or what one period will look like here. C is still going to represent our phase shift to the left or to the right. And then D, I have to sneeze, I'm so sorry. D is still going to be our vertical shift, either up or down. Alright, so how do we graph these? Typically, I would ask you to graph one cycle just because it happens so fast. It seems kind of redundant to do it multiple times, but in graphing the one cycle, the important thing to remember is that tangent is centered about the origin. So we kind of want to use that origin as our reference point. Now if we do shift, if we want to apply any of our translations, again those are our shifts to the left or to the right or up or down, and then find the new center. So if we go left or right or we go up or down, again we're going to have a new center. We would use that new center like we would use our origin. And then we have to use our period, okay? If we look at one cycle, we said the period is pi. So this period of pi here, well, half of it is to the right, half of it's to the left. So if I know what my period is and I know where my center is, I would go half of that distance to the right, half of that distance to the left, and that's where I'm going to put my asymptotes. So I'm going to go half of the period, and remember here our period is found by taking the pi that's in our normal and dividing it by b. We're going to go half of that to the left and right of the center, whether that's at the origin or translated somewhere else. And then those are going to give us the locations for the asymptotes. So we'll have, think about what's going on. We will have our center and we'll have the asymptotes. And I know that tangent is supposed to be an increasing graph. Unless it's reflected, then that would be upside down. So that's basically the picture. But we can be a little more precise because we have other points here. So this point here and this point here. In the normal, we go over right in the middle of our asymptote and our center, right in the middle of that. We go up 1 unit. So right and up 1, or we can go left and down 1, and we can get 2 more points to make a nice, really accurate picture. If A is something like 2, then we're going to go over to the right and up 2, and then over to the left and down 2. Or if it was 4, we would go over to the right and up 4, and over to the left and down 4. Again, that distance in between the center and the asymptote, right in the middle to the right, right in the middle to the left, but A tells us exactly how far up or down to make that next point, and then from there we just make our increasing or decreasing if we reflect it. So hopefully that makes sense. Again, I'm making a mess of my picture. So between the center and the asymptotes, we can plot 2 more points. We're going to go up A units to the right and down A units to the left, right in between the center and the asymptote. So again, if A is 1, like it is in the normal, we would just go over and up or down 1. If it becomes a 2, over and up or down 2, and so on. And then we should be able to make our one cycle. So let's try it out. Okay, we're going to try to graph. And my paper's not moving. There we go. Trying to graph, again, just one cycle. What is one cycle going to look like? So talk about the transformations here first. This guy, plus 2, is going to represent a vertical shift of our graph up 2 units. And then this is a phase shift. When we subtract, that means we're going to go to the right. And in this case, we're going to go to the right, pi over 2. And then, I'm sorry about my sniffles. The period has not changed here. The period is still going to be pi, right? Because b is still going to be 1. So I think we have everything we need here. Normally, we want to think about, this is like what one cycle looks like. Between negative pi over 2 and pi over 2, centered at 0, 0, right, and then up 1, left, and down 1, and this is what one cycle is going to look like. Okay, so that's the picture that I want you to be having in your head. Now what we have to do is apply the transformations here. So if we want to go up 2 and right pi over 2, up 2 and right pi over 2, this is going to be our new center. Okay, new center right there. So if our period is pi, half of that would be pi over 2. So the period hasn't changed. We should still be going pi over 2 to the left of that, pi over 2 to the right of that, and that's where our asymptotes are going to be. So we go half a pi to the left, make an asymptote. Pi over 2 to the right, make an asymptote. And then we're going to get 2 more points by going a units to the right and a units to the left of that center. Oh, sorry, we're going to go left and right of that center and a units up or down. So I think I thought I worded this wrong, but this is correct. Up a units and then to the right, and then down a units and then to the left, but in between the asymptotes and the center. So a is still 1 here, okay? So right in between, this is really hard to show you without pointing. Take this distance right in the middle of that. Because a is 1, we're going to go up 1, and then right in the middle between these would be here, and we're going to go down 1 and get us 2 more points. So we're looking at a big mess on the graph. So to the left, in between the asymptote and the center, and down 1. To the right, between the asymptote and the center, and up 1 because a is 1. And then we just sketch our little branch that's going to approach the asymptote. So something like that, and that's one cycle. And then if I asked you to graph more from 0 to 2 pi, you would just keep creating the same pattern until you got to 2 pi, but typically one cycle is going to be enough. Okay, so there it is, not too terrible. And I could obviously try to apply more transformations there, but I don't want to get too into these. Honestly, of the 6 functions, cotangent and tangent, not as commonly occurring in real-world situations that we will eventually get to. So let's go and turn our attention to the cotangent function. Parent for our cotangent function is y equals the cotangent of x. Now, we hopefully remember that cotangent is just the reciprocal of tangent. So the function can also be written in the form y equals 1 over the tangent of x. Now, the tangent of x was sine over cosine, which means we could also write the cotangent as cosine of x over sine of x. So they have 3 functions that would all produce the same graph. Cotangent is the reciprocal of tangent, which we could say 1 over tangent, or since tangent was sine over cosine, this could be cosine over sine. Now, we already saw also what happens with our reciprocal functions. Basically, the reciprocal behaviors, right? Where one graph would be increasing, we should now be decreasing. And let me go back here for a second. In our tangent function, every place where cosine was equal to 0 is where we have asymptotes. In the cotangent function, everywhere sine is equal to 0, we are going to have asymptotes. So since we know what sine looks like from 0 to 2 pi, we should be able to do this graph based on sine and our knowledge of what we just did with tangent. So sine, remember, starts at 0, ends there as well, and hits a 0 in the middle. So sine would have, hold on, getting ahead of myself. If I was graphing a sine curve, it would start at 0, end at 0, hit 0 in the middle. Any place sine is equal to 0, cotangent is going to be undefined because that would put a 0 on the bottom of the fraction. So I know my asymptotes for cosine are going to be at 0, pi, 2 pi, and so on. And then in between the asymptotes, we're going to have the same thing that we just had with tangent. We're going to have a center point, and in the parent form, right and left in between, right in the middle of the asymptote and the center point, and down 1 or up 1, but in this one, the reciprocal behavior. So instead of an increasing branch, we're going to see a decreasing branch. So I'm going to go to the left and up 1. I'm going to go to the right and down 1. And this is what my one cycle is going to look like. And I'm just going to repeat it. Center, left and up 1, right and down 1, and there it is. So there's 2 cycles that happen here, again from 0 to 2 pi, but the one cycle that I want you to be thinking about visualizing in your head right there. So for tangent, again increasing, here decreasing. Rest of the properties are basically the same. It's just the location. This is just moving the asymptotes and switching the direction that the graph is going. So again, we see something here that is not continuous. This time, we have our vertical asymptotes where the sine of x is equal to 0, and that happens at our... Oof, I'm so sorry. I'm having issues, just don't mind me. Where the sine is equal to 0, and that happens at our multiples of pi. So sine at 0, at 1 pi, at 2 pi, all those places we have asymptotes, those are the easy ones. At n pi, again where n is an integer. Here, between the asymptotes, we have the branches that almost look like cubic functions that are constantly decreasing instead of increasing. Again, we have a period of pi. It only takes half of our normal window. We're used to looking at 2 pi for the pattern of y values to repeat. The x-intercepts here, so this is just flip-flop from tangent. Tangent was where cosine was equal to 0, the asymptotes, and then the x-intercepts were where sine was equal to 0, and here it flip-flops. Sine being 0 gets us our asymptotes, and here where cosine is 0 is where we have our x-intercepts. So the x-intercepts at the... change to pink. The x-intercepts here happen where we have the odd multiples of pi over 2. So at 2n plus 1 pi over 2. And again, no max, no min, no amplitude, because we have branches that are going to go up and down forever. So domain has to exclude the asymptotes. So all... that was not a good bracket. I don't know about you, but I struggle drawing those. So we have all x's such that x cannot be a multiple of pi. And the range, unrestricted. These graphs go up and down forever. Any y value is going to be possible. Everything from negative infinity to infinity is going to be in there. And cotangent, just like tangent, and I could put it in here so you can see it, the symmetry about the origin. If I graph y equals the cotangent of x, again looking at the origin, it's every point and its opposite. So the cotangent of negative x is equal to negative cotangent of x. So when I plug in a negative, I get a negative result. Unlike the evens where plugging in a positive or negative yields the same result. So still an odd function that's got symmetry about the origin. Now let's talk about our transformations. Basically doing the same thing here. Okay, we've got a vertical stretch possibility, horizontal stretch or compression possibility. We just don't apply those terms. We don't apply this to an amplitude anymore. We'll just call it a vertical stretch compression. This still affects the period, but it's now pi divided by b. This is still representing a phase shift, and this is still representing a vertical shift. Now cotangent. Tangent starts at the origin. We have that point on the origin. Here, cotangent has an asymptote through the origin. So I like to start with that as my reference. And then if we have any translations, are we going to shift up or down or left or right, we'll apply them to put in our new asymptote. And then instead of, because I have an asymptote, I'm going to go the whole length of the period. Right, if my period is pi, I would go the whole length of that asymptote to get to my next one. So go the whole length of the period left or right to draw the second asymptote. And remember, period is just 1 pi divided by b. And then we're going to plot the center point between the asymptotes. I don't know if I needed a blank there. Sorry. And then between the center and the asymptotes, we can plot the 2 more points, down a units to the right, and then up a units to the left, so the opposite direction because we're decreasing this time instead of increasing. And remember, a becomes a 2, then we're going to go up 2 or down 2, and if it's 3, and if it's a half, up a half, and down a half, and so on, just so we can make a little bit of a more accurate branch. So let's try. Okay, let's identify the transformations first here. This is going to be a vertical shift. That's going to make everything go down 2, 2. That's going to be a vertical stretch of the graph. And again, from our center point, when we go left and right, we'll go up and down 2 units. And then here, because b is equal to 2, our period is going to change. Normally it's pi, but now we're going to divide that into 2. So pi over 2 is how long it takes for just one cycle to happen, and that's what we're going to try to graph here. One cycle. So normally, again, just let me get you a picture of the normal, right? Normally one cycle has an asymptote through the origin, or like on the y-axis there, and pi over 2 units. Oh, this one is very stretched out. I stretched this graph out because we're doing multiple, but let me do the picture over here. So normally we're on the axis, and we would go out pi units, which will be over here, to make our 1 period. Here's our center, and then we'd go 1 and 1 and make our curve, right? So that's normally what we're going to do here. But this one is going to shift. Now, if we shift, why did I say down 2 over here? If we go down 1, that's not going to move where our first asymptote is. So my first asymptote is still going to be, I don't know why I stretched this out. Oh, I know. Sorry. It's still going to be here. Now our period is pi over 2. So instead of going a full pi to get to my next asymptote, I only have to go pi over 2 units to get to my next asymptote. So I'm going to put that in there. Now normally we would be on the x-axis to make our center point. I'm trying to think of what something was supposed to be in that blank. But here, because we're shifted down, like normally our point would be here, because this is shifted down 1, we're going to make that center here. And then from there, because a is 2, I'm going to go in between the asymptote and that center point. I'm going to go to the left and up 1, 2. So left and then up 1, 2, and that will be a point there. And then I'm going to go to the right in between that center point and the asymptote and go down 2. So 1, 2, that would be there. And now I can connect. And this is what my one cycle is going to look like. And it's always nice to have technology to confirm what we're doing. So let's go ahead and put it in here. Y equals -1. That's not an equals. -1 plus 2. Goodness. 2 cotangent of 2x. Okay. So I just want to focus on 0 to pi over 2 and see, does that look like what I did? So 0 to pi over 2, I can tell I have an asymptote at 0 still. I can tell I have an asymptote at pi over 2 still. Now I want to try to confirm, is there a point on my graph at pi over 4 and -1? So if I want to be sure, let me go ahead and put that coordinate in here. According to my shift, that's where it should be. So at pi over 4 and -1, do I have a point on my graph? And yeah, so you can see there's the center point that we plotted. Now I also plotted a point, you don't have to go through all this work to check, but I just want to show you that this is pretty accurate. Between 0 and pi over 4, that would be 1/8 of the pi. So at pi over 8, coordinate. At pi over 8, and we're at 1 there, we should have another point on the graph. And yeah, so you can see that point on the graph, the one that I plotted on my paper, I just confirmed that in Desmos. And then 1/8, 2/8, 3/8. 3 pi over 8 would be where I made the next one. Again, this is a coordinate. I just am confirming my work here. And that should be at -3, according to what I did. And yeah, looks good. So you can, again, use your calculator to confirm. Maybe if I stretch this out, it looks a little bit better. Oh yeah, now you can see it a little bit better too. But yeah, so use technology to confirm what you're doing. Generally, again, I shouldn't say this, but we don't typically see tangent and cotangent occurring as naturally as we do with some of the other functions. And so when we get to applications later on, you won't see as much of these. So I don't want to focus too much on these graphs. If you kind of know what they're supposed to look like and you can graph one cycle, you're going to be fine. So identify the transformations, do your best to make one cycle, use technology to verify what you're doing, and as always, reach out if you have any questions. Alright guys, till next time, take care.